All right, hello. I'm Skyler Cartwright. My group is me, Lane, Caden, and Cody. We are doing our presentation over light and lighting. The sections we'll be going over are light and the energy spectrum, physics of light, vision and the visible spectrum, color, and means of controlling light.
All right, so the first thing we're going to talk about is light energy conversion, which is newer technology, more like solar panels, stuff like that. How it's going to work really? It's when light comes off the sun, it takes the waves, able to go into this panel and convert it to energy for houses, electricity, stuff like that. A lot of companies actually go into, such as like Tesla, are going into advancements on how to make this more efficient. As of right now on the market, you can only get about a 27% efficient um, electricity coming out of the sun. But they do have studies going to 40%, but they're not available in the market yet. A lot of companies are researching and growing into it to become more efficient for everyday use. Other versions of stuff like photosynthesis, plants take the waves itself and convert light into chemical energy. All right.
All right, so physics of light and photometric quantities. These are some of the scientific terms. I will be trying to refer to the names more often used rather than the scientific ones. Some of the units of light, lumen, candela, foot candle, foot lambert, candela inches squared, and then per unit. Light energy. Energy can be converted to light through means of electrical, like light bulbs, heat, such as space heaters, chemical, different chemical reactions and stuff. Some of your light bulbs actually use chemical reactions to produce light. For this, light intensity and power, your visible spectrum. The intensity of light is kind of the way we view it, and how our eyes view things differently, whether it be during the day or at night. Like car headlights during the day don't appear very bright. At night, they appear a lot brighter. For this, luminous flux and light intensity, it's the way we view light, how intense it is. Illumination, we see the different colors of light. Brightness is kind of the way our eyes perceive light, as back to the vehicle headlights and appearing brighter or dimmer depending on the time of day or brightness of the bulb itself. Different laws, you have the inverse square law, which is the top one. It shows how a light source at a closer distance only projects over, say, a 1 foot squared area, versus further out, it will cover an entire 9 foot square area. And then you have the cosine law, which is light coming in at an angle will cover a wider area than if it's directly shining on an object. Luminance, the term brightness is often used in place of luminance. These terms are not the same. They're kind of day versus night. Luminance is kind of like your illumination light bulbs, stuff like that. Brightness is something we as humans and our eyes attribute to it because more of the way we see it. Luminance existence is flux leaving a surface. It's reflective. You have the reflective, and then you have transmitted or translucent surfaces. This slide is for contrast. I did the slide black with gray lettering to show you can still read it, but it's a little harder to read versus this slide where I did it as black with white lettering showing contrast being as I show black versus black and white and black and gray was the easiest way for me to explain this one.
Okay, my name is Lane Ardoin, and today I will be discussing vision and the visual spectrum. Some of the topics we're going to go over are visual comfort, glare, modeling, and the visual spectrum. And first, we're going to get into visual comfort. Why is it not? Okay. Click next on it, Skyler. Visual comfort refers to the reaction of quantity and quality of light in a given area. If you'll notice, most schools and businesses today try to catch as much natural light as possible with many windows, and then, of course, having adequate overhead light as well. And a high visual comfort plays a key role in providing a productive, concentrated working environment. But there is a such thing as having too high of a visual comfort, and this is when you start to experience what we call glare. Glare is when the luminance of a light source on an object is so high that it begins to interfere with vision. And there's a few different types of glare we're going to talk about today. The first type is discomfort glare, which is the glare that is strong enough to cause physiological discomfort. Next, we'll talk about disability glare. This is when a glare actually affects your ability to see. And then we'll talk about direct glare. This is a glare that comes directly from a light source. And then lastly, we'll talk about reflective or indirect glare. This is when a light source is reflected off of a surface and into your face, causing discomfort. Next, we're going to talk about modeling. Modeling is just the ability of a lighting system to reveal the 3D image of an object. And modeling is very important in the construction industry because it provides a solution to the limitations of horizontal and vertical lines, vertical and diagonal lines in two-dimensional sketches. It gives it a sense of depth. And then lastly, I will be going over the visual spectrum. As Cody stated earlier, the visual spectrum ranges from 380 to 780 nanometers in wavelength. The visual spectrum consists of many different colors of light, and the reasoning for the different colors of light is due to the different wavelengths of color. And if you look at this graph, I thought it was interesting when I was doing my research is none of these colors just hard transition. They all blend as they go across the spectrum from infrared all the way down to the ultraviolets.
All right, my name is Kaden Keller, and I'm going to be covering color. Color is a matter of visual perception. It varies with a person's subjective interpretation. Let's say, for example, an apple can be described as red, dark red, bright red, or even apple red. However, this is only a general description of that color. So next there's three basic characteristics of color. You have hue, which is the basic colors, red, blue, green, and so on. You have value, which is going to be the shade of that color. So dark blue, bright red, dark green. And you have chroma, which that's going to be the intensity of color saturation, which is the color. Is it vivid? Is it dull? What does it look like? Next on, we're going to go into color systems. The first system we use is called the Munsell system. It's a method of notation for describing the color of an object or a surface. Usually uses two color charts. The first being the 20 basic hues of saturated colors, and the second color chips of the basic hues, but with different values and chromas. So as you can see in the examples there on the right, you have different chromas for each color. And on to color systems, the CIE color system is a color system for lighting applications. It uses the chromaticity diagram. All colors can be found on this diagram, and they're expressed in the X and Y coordinates. However, all saturated colors can be found on the outer perimeter of the diagram, known as the spectrum locus. Next on to color temperature. Color temperature is measured in Kelvin. As you can see in that one diagram on the left, a high temperature color that we usually see would be daylight at 6,500 Kelvin, all the way down to a soft, warm color that you usually see in restrooms or bedrooms at 2,700 Kelvin. On the right, you can also see when you walk outside, you're looking at approximately 10,000 Kelvin versus a candlelight at only 2,000 Kelvin. On to color rendering. So the three primary colors are red, yellow, and blue. When mixed together, you create white light. Depending on the mixture of these three colors, other objects in the room will appear different to our eyes. So, as you can see on the left, that is a fluorescent light bulb, which are rich in blue, lacking in yellow. They appear more white. On the right, you see an incandescent light. They're rich in yellow and red, but lacking in blue, so they appear a warm, more yellow color. So color selection plays a huge role when they're designing buildings. So you usually see warmer light sources generally used to enhance warm colors like red and orange. Meanwhile, cooler white light sources are used to enhance cool colors such as green, blue, and purple. You also usually use cooler white light for manufacturing plants, places you need to see everything, versus yellow light for restaurants.
I'm going to finish it off with methods of controlling light in the construction atmosphere. Good. Now, how light travels can be all different. I'll reflect, absorb, transmit, refract, diffuse, or polarize. First, we're going to talk about reflection. Reflection is going to be off any kind of shiny material, such as a glossy paint, metal, or a mirror. Now, this is what it's going to do. When the waves hit it, it's going to bounce off at a 45-degree angle and reflect all light, pretty much the full power off it on a different direction. Next is going to be absorption. Any kind of opaque material is going to take away the light itself. Any kind of dark, for example, this door itself is going to, when the light hits it, it's going to absorb. It's not really going to reflect at all, keeping the material in the room itself dark. And then you have transmission. Transmission will be used mostly like in a concert where they can put lenses over these lights to help kind of control the mood of different songs, different kind of scenarios that they do. So with that white glass, you can still see through it pretty clearly, but it has a little bit of light taken away out of it. Then you have refraction. That's simply the bending of the light. And Isaac Newton did an experiment back in the day where he got a glass prism just like this, put it out where he can see in the sun and reflect on a piece of wood. This light coming in actually gave the spectrum, the visual spectrum, as you see there, showing that there's more than just white light. It's all different colors combined. You can do this same example as with a water bottle, with a spray bottle. You shoot in the air, you'll see the visual spectrum, the rainbow actually right in front of you if you want to do it yourself. Then you have diffusion. This is going to be a great example. It would be like a greenhouse. If you have a regular window in there that's not a diffusion window, light's going to come through and travel the same direction. The waves are going to go the same direction, and you're actually going to get shadow on some of your plants. So the plants won't get the light it actually needs to grow. With diffusion, you put that lens up there, and it will send the light waves absolutely everywhere. So once you go into a greenhouse, there actually is no shadows casted because of the way that this light's diffused. Then you have polarization. The most common polarization is going to be sunglasses. And how that really works is the way the lens made, it actually can cancel out the waves. As you can see the waves here, the yellow and blue waves. Once it hits the lens itself, the blue waves actually go away because the lens is actually canceling it out. Go on. So kind of give it away at the end on the real life experience. I actually got the pleasure of doing an internship over the summer at SAM with one of these companies doing construction. We did a little bit of drywall. And one of the light problems we came in, as you can see here, those white lines is like a putty in between drywall that makes the wall look like it's as slick as possible. It's called a level 4 finish. So you go ahead to the next one. So this project that we actually worked on was underground in Houston. It's the jury assembly. As you can see, it's a really dark room and no windows because it's all underground. So the architect wanted everything to be shiny, bright. So their thing was they're going to use a gloss paint to get the reflection everywhere. So when light hits it, it's going to go everywhere and light this whole place up because the brick's going to take away from it. So we did a level 4 finish, which is not, clearly all high enough to get the good cast, smooth finish on it, because with the level 4 finish, when light reflects off it with a gloss paint, you're going to get some kind of shadowing from the reflection. Then you're going to see any kind of imperfection going on to it. You can go to the next one. And such as like this, using the direct lighting, that's what's going to cause it. And you can kind of see the waves in this picture itself, but this is not painted yet. If you go to the very next one, this is when the paint finish on it. You can actually see the imperfection in this left-hand picture of the bumps. So being the bumps there, the ideal of the architect is to sell the job as perfect as possible. And something like this, wouldn't be acceptable in the field. So we ended up having to go in, do a level 5 finish because they wanted to keep that gloss paint for the reflection of the light. We're doing a level 5 finish, actually made that wall way more smooth, looking more professional, more professionally done, where they could sell it. Being with that change order, just because of the light issue, would have been a $30,000 change if they wouldn't have actually caught it at first hand. But that's going to be the end.
And here's our references.